Hi, now let's discuss about the remaining type of sensors for bioinstrumentation, electrical sensors and optical sensors. So first, I want to describe electromagnetic spectrum, which is described in this rough diagram, that there is a shorter wavelength to longer wavelength. All electromagnetic waves are produced by electron acceleration, especially periodical motion. So you can see from UV, ultraviolet, to visible light, which is about 400 to 700 nanometer wavelength range, and IR, it's infrared range. So our visible light is only a very narrow part of the spectrum, which can be visualized and recognized by our eye, especially the retinal system of cones. So let's start with the electrical sensors. So we can use electrode to detect electrical potential of our body parts, especially like heart, that we call as electrocardiogram or ECG or EKG. That ECG measures the electrical activity of the heart through electrodes non-invasively put on the surface of defined location of our body. So such as you've already seen this ECG. And the next is a cardiac pacemaker, or we call artificial pacemaker, because our heart has its own pacemaker called SA node and AV node. We have developed this artificial pacemaker, which is a medical device to regulate the beating of the heart or heart rate using electrical impulses, which is delivered by the electrode. You can see here a pacemaker is implantable, and that electrode is going through these veins and to right atrium and right ventricle, so that it can provide a regular heartbeat for those who has a problem with the heartbeat, or we called it as a arrhythmia. So the next is about defibrillator. So when a person has a cardiac arrest, so that is an emergency case, and we can use external electrical shock to reset the heart and regain the proper rhythm. So that is called AED, or automated external defibrillator. And this is a portable electronic device that automatically diagnose and correct cardiac arrhythmia of ventricular fibrillation. So you can see a person, let's say, has a cardiac arrest, then this portable device, you attach it in a proper location, like here and here, that's kind of going through the heart, then it will analyze the data of the heartbeat, and then it can decide to give a shot for this arrhythmia, which is caused by, in this case, ventricular fibrillation, which is a very important dangerous condition. So that we call arrhythmia, or irregular heartbeat. So now let's discuss about optical sensors. Before getting into this, I want to discuss about photoelectric effect, which is found in the long time, more than 100 years ago. So there was a phenomenon observed that on a metal surface, when experimenters send a light, such as visible or UV light, and that light rays somehow eject electrons from a metal surface. So those are electron emission. That is, at the time, only Maxwell's theory was prevailing, so that we understand the light as a wave. And when, let's further to see, when the light frequency or the color has changed into a longer wavelength or a smaller energy, and somehow these photoelectron did not coming out, even if we give a lot of intensity, which means a lot of photons from our understanding. So this effect is called a photoelectric effect. So why we are talking about this in optical sensors? Because we use this a lot for detecting light in the UV, visible, or infrared regions of electromagnetic spectrum. So this effect is called photoelectric effect. And when the metal surface is struck by light, and its atom can emit the electron, and that is called photoelectron. And the problem is this effect could not be explained by wave theory of light, because at certain wavelength or higher wavelength, even there's a lot of photons, lot of light intensity, it never give out photoelectron. It wasn't understood until Einstein explained this as a beam of light is not a wave, but a collection of photons, and introduced the energy to this single photon as Ha nu, and which is described in here. H is a Planck constant, nu is a frequency of the light. So that electron is, so this effect of the metal is we call photocathode. Cathode is a place where electrons will be ejected, okay, depart. So metal surface on which the beam of light is shown and emits electron. And that electron is we call photoelectron, which is ejected from the metal. And of course, electron, as you know, electron is a particle with a charge, negative charge. And that electron flow of electron over time, we call it as a current. So we call this as a photocurrent, which is shine a light on a conductive metal surface that can cause a flow of photoelectron, and that, you know, over time, the amount of charge is called electrical current. So that Einstein's explanation of this as a photoelectric effect and introduction of the concept of photon as a light as a particle kind of changed the whole idea and introduced the emergence of quantum mechanics. So that particular paper was proposed in 1905 on a heuristic viewpoint concerning production and transformation of light. And because of this, Einstein got Nobel Prize in 2021, not for his even more famous discovery of special and general relativity. So the experiment shown, this photoelectric effect is shown here. You see the light with a filter having only this blue or specific wavelength of light comes in, and this is a cathode, okay? And that electron ejected will come out to this electrode, and you can measure the current, and you can change the voltage to measure this binding energy or work function he proposed later. So now I'm going to describe two kinds of optical detectors, which is prevalently many times you are using in the laboratory environment. So first is a photo multiplier tube. What does photo multiplier tube mean? Because it looks like a tube. This is inside a vacuum tube, which is kind of rare in this modern age, but yes, we do still use this photo multiplier tube, or we call it PMT. And if you look at inside, and this is a simple diagram, although it looks a little complicated, but let's take a look. When the incoming photons get in, you see there is a photocathode. So this will eject a photoelectron, and that photoelectron is a negative charge. So you actually have a very, very negative voltage applied on this, so that the electron accelerates to hit this metal surface, and we call it as a secondary emission, that photoelectron ejected, and another probably about 100 volt higher than this, so that the electron moves toward hit, and then there's a more number of photoelectrons, and we do this over and over again, reaching this final electrons getting into this electrode, we call it anode because this part is cathode and the other part is anode. So a huge amplification or multiplication of photoelectrons getting in to generate a photocurrent. So that's the principle of photomultiplier too. And you can see how we can make this, like, let's say 100 volt higher, reaching to the enormous multiplication, which is about 10 to the 5th to even 10 to the 8th, like 100 million times higher number of photoelectrons to create a current. So PMT generates a vacuum tube that converts the instant photons into the current. So to generate this, you need a circuit with a high negative voltage power supply, and then you have this voltage dividing circuit to provide, let's say, minus 800 volt, minus 700, minus 6, 5, 4, 2, 1, 0 volt. And then you collect those photoelectrons. So PMT is incoming photons are absorbed by photocathode, generating electrons by yes, here comes photoelectric effect. And the current is amplified by cascade of electrodes. We call this, in the middle, this electrode as diodes. This is just a historical reason to put this diodes name. And what's interesting here is the PMT has a high sensitivity, even single photon sensitivity that it provides. So this is a real proof that the photon, the light is composed of photons, okay? Single photon sensitivity with a available photon counting mode, which means because it's a photon, even single photon gets in, we detect the signal, then we can even count the photon. This photon counting mode is very useful in very low light condition experiments. Then each single photons can be separated, and in the middle noises can be eliminated by comparison with a threshold. We call it as a discriminating photons from a noise. Okay, so I just want to have an expanded picture of this. You can see these are the diodes. Can you see? That's similar. So where do we use the PMT? So PMT is used for very low light level spectroscopy, UV visible spectroscopy, and also in microscopy, especially laser scanning microscope, which we detect photon from each single pixel over time. Sequentially, we use PMT. So confocal microscope to photon microscope, and even in medical imaging and a basic science, in astronomy to detect photons or gamma rays, in medical field, radiation. These we can also use for medical imaging with these PMTs. And the second one I want to describe is a little more more prevalent because it's cheaper. That's called photodiode. And it looks like this photodiode. You see this 1 centimeter. So photodiode can be very small. These are silicon photodiodes. And what are photodiodes? It converts light energy into electrical current or voltage based on how we apply our circuit. So a good example of photodiode is actually solar cell. You know, the solar energy generate electrical solar power as a large photodiode. So that's what you can see, understand as a photodiode. So when photon strikes the semiconductor material such as a silicon or a gallium arsenide, and then photocurrent is generated by, again, photoelectric effect. So here is a symbol for this. So what it means is when photon gets in, then from anode to cathode, there will be a current. A good example for this is finger finger pulse oximeter, which I will discuss later. And there we use LED and photodiode because it's very tiny. You can make it small. And that resulting voltage is proportional to the intensity of incoming light. So this is a more of a the insight for photodiode. There's a P types, there's N types. N types, there's an electron. P types, there's a hole pair, and you can put a bias voltage, and that external light will create a photo current. And I want to show that an exemplary data sheet for dependent on the wavelength, and this is in silicon photodiode. You can see the response as the incoming light power of the light, you will generate a corresponding ampere, which is a current. And you can see the response curve seems like it's the most sensitive around 900, like 50 here. And it's a little lower and lower into UV regime, and you can detect only up to about 1100 nanometer. So higher than that, it's hard to measure using this. So because I introduced PMT and photodiode, I just want to give you a sense of comparison. This is reference. So when do we use photodiode in comparison to photomultiplier tube? So photodiode has an advantage of excellent linearity of output current as a function of incident light input or intensity. And you can see this is a much lower cost compared to this PMT, which is inside this vacuum tube and very delicate. You can't shake, you can't drop this because it will break. So while photodiode is much compact and lightweight, and it just lasts pretty long lifetime. You don't need to worry about lifetime, and higher quantum efficiency, and you don't need to provide high voltage to run this like in the PMT. As you say, you do need a separate high voltage power supply to run PMT. And then disadvantages of photodiode, of course, is a more of a, could be advantage of PMT, which you see the active area can be very small, while PMT, you can generate this photocathode as pretty big. And this is a side view, and this is a frontal view of PMTs. And photodiode do not have an internal gain except avalanche photodiode, while PMT has a huge gain mechanism. As you remember, there's a multiple diode which multiply the photocurrent. And photodiode has an overall lower sensitivity compared to with the PMT, and it's a slower response time. And so because of that, it's a low sensitivity. You can count photon in general with photodiode. So their applications can be a little different. So with this, next time I'll discuss about instruments in medical practice. Thank you.